Good morning, everyone. Welcome to the class again. I'm sure you had a wonderful weekend. Um, Today, I'm going to talk about RNN backpropagation through time. This is the subject of class today because backpropagation is the basic and most important part of the machine learning model. So I'm going to spend quite amount of time to derive all the equations. Especially today, I'm going to talk about the RNN backpropagation. And Wednesday, I'm going to talk about LSTM backpropagation. It will take a lot of mathematics and detailed derivation of equations. I hope you keep patience and keep up with the progress of class today. From next week, I'm going to talk about autoencoder, generative advisory network, DC GAN, and finally, I will talk about reinforcement learning. During the course of reinforcement learning, I'm going to talk about policy gradient, Q-learning, and reinforcement algorithm. Each of these subjects are not easy to understand, but by having good concept and idea about all these machine learning models, you will be more confident and you can use them for your real applications. So the level of class in after midterm will be much higher than the level of classes before midterm exam. So I hope you put patience on the progress of class today. Now, let's talk a little bit about the RNN. In this figure shows the basic structure of RNN. As you see that it has sequential input x1, x2, and up to xt. T means terminal. T could be thousand numbers or could be millions or billions, depending on how much sequences you're gonna use for training this RNN structure. If you have X input, that will be connected to hidden layer H by multiplying matrix U, then hidden layer will be connected to output layer by multiplying matrix V. By applying the softmax, we will obtain output Y from O1. And then we can calculate cost function J. However, hidden layer output of stage 1 will be connected to hidden layer of H2 using matrix W. So the informations of previous states will be carried to next and next stages by having these UW matrices. Again, at stage X2, will be connected to hidden layer H2 at stage 2 by applying U matrix and by having input from previous hidden layer multiplied by W and input X multiplied by U, we can calculate hidden layer H2. Then hidden layer H2 is connected to output layer O2, and then by applying softmax, we can obtain Y2, and eventually we can obtain cost function J2. In the previous machine learning models, we usually have single cost function, but in this RNN, we have cost function from J1, J2 to Jt. That is the basic structure of this RNN. So in order to apply the backpropagation, we have to define cost function J1, J2, and J3. And by applying the chain rules, we can update V, W, and U. You remember that in RNN, this V matrix, W matrix, and U matrix are repeatedly reused at the next stages and next stages. Meanwhile, you remember that during the backpropagation, we have to update this V, W, and U. In this class today, I'm going to show you the progress to update the train V as well as W. In the case of U backpropagation, we start from cost function and we go through this softmax function and we update V. However, in the case of W, we have to calculate cost function J2 and we have to go through all this chain rule to calculate and update W. Also, in the case of JT, in JT also we have to calculate cost function and we have to find a chain rule to update these W's. So updating the W is much more complicated because it is sequentially connected from cost function JT2 up to hidden layer H2 and H1. So because it goes it goes from JT to stage 1. So W is multiplied T times. That's why we call this backpropagation is called backpropagation through time. So these are the just simple overview of class today. This is a little bit complicated. I spent a week or 2 weeks to derive all these equations. It is not easy to find a textbook. So I'm going to show you them today. So anyway, during the backpropagation through time, we have to update W by using the gradient descent equation. In order to apply this gradient descent equation, we have to find an equation to describe derivative of J with respect to W. When you are updating U matrix that is shown up here, then we can use this gradient descent equation while alpha is the learning rate. In order to update U, train U, we need to calculate derivative of J with respect to U. In a similar way, when you are updating V, also you have to be able to calculate derivative of J with respect to V. So what is the meaning of backpropagation through time means you have to derive all these equations. By applying multiple data for training, we can keep update 1,000 times or million times of this gradient descent equation. Eventually, we can optimize W, V, U, and V. That is called backpropagation. In addition, I would like to remind you that Y is obtained by softmax of output function at stage T. Please remember that. In order to obtain derivative of J with respect to W, we have to have all these equations because we have to apply the derivative relationship of the softmax function. And output OT is obtained from hidden layer HT by applying this V matrix. And also in the RNN, cost function at stage T is a cross-entry function of output Y. This is the target value, usually 1 or 0, depending what is the real output, target output, true output. And this is the log of the output function YT. You remember that this is the cross entropy cost function. And one interesting thing is that in RNN, we define total cost function. That means at each stage, we have a cost function. Cost function at stage T is coming from cross-entry function between the true value and our output value. In the previous classes, we was talking a lot about the physical meanings and mathematical meaning of cross-entry function. And by having on cost function at stage 1, that is not all. We have to summarize all this cost function. That is going to be total cost function of RNN. And these are the basics of backpropagation in RNN. So because now we have connections in this slide, we know this structure, and we know the equations, and then what we're gonna do is to derive this derivative of this cost function with respect to the unknown parameters u, v, and w. That is gonna be the sequence of our class today. Now, once again, this is the overview of the RNN backpropagation through time. I'm gonna go step by step today, so be patient. Now, once again, as I mentioned in the previous class, uh, in order to update u, v, w, and v, we have to define the cost function. We have to define the cost function. For cost function in RNN is defined sum of cost function at each layers, each state. At each state, s equal 1, t equal 1, t equal 2, t equal t. At each state, we define the cost function j1, we define cost function j2, we define cost function jt. So what we have to do is we define the total cost function. So in order to update, for example, v, we have to find the derivative of cost function with derivative of with respect to v. V is the scholastic representation of the matrix connecting between hidden layer to output layer. And then derivative of total cost function with respect to v is the summation of derivative of cost function from t equal 1, t equal 2 to t equal to terminal. So this is the final expression of the total function and derivative of cost function. As you remember that if you want to update v, v should be updated by this equation. This is the gradient, this is the equation. This total gradient of cost function with respect to v can be obtained from this. In the previous classes, uh, I was driving the chain rule equations of back propagations. In those cases, we had a single cost function, but however, the difficult part of the back propagation equation in RNN and LSTM is that cost function is the summation of cost function of each state. So it will make very complicated. For example, if you want to update the W, you have to think about path of this one and path of this one. In the path of this second path, you have to find all the relationship from t equal to t equal t. That is the very complicated chain rule equations. And those are the subject of class today. Now, in this slide, I was talking about the definition of cost function. Once again, I want to remind you that hidden layer output is tangent hyperbolic function because activation function of RNN is usually used using the hypotangent hyperbolic function. So later on you will have to find out tangent hyperbolic function derivative. And later on we will do that. And the input of this hypotangent hyperbolic function at state t is multiplication of U matrix with the input vector and W matrix multiplied by the previous hidden layer. That is the property of, let's assume we have HT, then we have previous hidden layer HT minus 1 and uh, present input vector is HT, and HT is multiplied by U matrix, and previous hidden layer was multiplied by W matrix, and that is gonna be input of this hidden layer, and we have to apply tangent hyperbolic function of this term, and that is gonna be hidden layer at stage T. That is the mathematical description of hidden layer. Output layer, here hidden layer will be connected to output layer T, and then the connection between hidden layer and output layer is described by matrix V, and YT is output of this RNN at stage T is the softmax function of OT. And the cost function at stage T is the cross entry function of true value and output value. Now that is the prerequisite requirement to derive all those chain rule equations for backpropagation through time. Now our task is my task is I would like to derive backpropagation through time equation for V. As you remember that V is the matrix connecting hidden layer to the output layer. So it is a little bit easy to do that. So I'm going to derive some equations to find the backpropagation through time. Once again, you remember that cost function is the summation of cost function jt from 1 to t, and then we apply that. So because j is described by yt, you remember that cost function is a function of yt, and then yt cost function output function yt is the function of OT output function. This is the cost function property, and this is soft max function property. And then you have to find the relationship between output function and the V matrix. That is the third term. That is the V relationship. So now we have three equations. Number one is the derivative of cost function. Second term is the derivative of soft function. Third term is derivative output function with respect to V. So what our task is, if we derive first function and second equation and third equation, we just plug them into this equation, and then we make a summation. That is going to be the total cost function derivative of total function with the derivative of V matrix. Then we can update the V matrix by using the gradient descent equation. So those are the sequences of our class. Now, what I'm gonna do is the number one task. Number one is the cross-entry function, and derivative of cost function with respect to y is minus y dash t divided by yt, because y dash t is the true value true value, that means in mathematical description that can be that is the constant. So we don't worry about that. Derivative of log yt with respect to y is the 1 over yt. You remember that log derivative log is 1 over y. So what we found is that number one, we obtained the number one. Derivative of cost function with respect to y is the minus y dash divided y. So we're gonna plug this number four equation to number one. That is the first job we have done. Now, second task is that we have to derive equation number two. Let's do that. You remember that cost function output is the summation of, let's assume that you have a output vector O1, O2, and OQ. And from that, we have to calculate Yj. So as you remember, the softmax function is defined using these equations, and each output number has the exponential input, and you have to summarize that this is equal to E1t plus E02t and EOQt over EOJT. So you have to plug in this O is plugged into the exponential term, and your J term is coming to here. So what we're gonna do is the derivative of this function. What I'm gonna do is the O I override or derivative Yj. So once again, I would like to say that this is the definition of cost function. For the simplicity of analysis, I'm going to consider a case where j is equal to I. So let's do the derivative of OJ, and then you remember that when you apply the derivation rules, first you have to do is the derivation of this first term. And exponential derivation of derivative of exponential term is itself. You remember that exponential forms, derivative exponential is the itself. That is the first term. Second term is that derivative of this kind of function is because this is denominator, thus then we become minus square, and then we have the derivative of x. This is the college level first freshman or high school level derivation. So derivative of second term is coming to here. Minus is coming here and square, and derivative of this term, we obtain this denominator. And then you remember that this one is Yj that is coming here, and 1 minus second term. If you spend some time, we can obtain that. This one is Yj again. So in simplicity, I would say that derivative of Yj with respect to Oj, Yj is output or the output of softmax function. Oj is the output of the RNN stage T. We will get this form. So derivative of even though this is not easy to do without spending all this time for derivations, but what I would like to emphasize is that derivative of Yj with respect to Oj is Yj 1 minus Yj. This is equation 5. that will plug into this term. And for the simplicity of explaining, I would say yj is the softmax function of OT. Of course, y is vector and O is vector. So that is the column, and the O vector also has columns. For simplicity of analysis, I'm not going to give you all the vector indexes j and I. I'm going to make it a little bit simple today. And then by applying the derivative of softmax, what I found is that that is yj 1 minus yj. So we're gonna plug in this equation 5 into this equation number 2. The last term, what we have to derive is the derivative of output function with respect to vector v. Now we have hidden layer that is connected to output layer using the matrix, hidden layer matrix V, and that is going to contribute the yj through the softmax function. So you remember that this is what we have to derive this equation. And you remember that output, derivative of output with respect to vector V is the hidden layer. So this is the number 7. So in the previous lecture slide, we derived the equation number 4 and we derived the equation number 5. The last thing is that the connecting element from H to O is vector V. So if you make a derivation of output function, output with respect V is actually hidden layer input. That is shown up here. So the conclusion is that derivative of J with the vector V, derivative of J with the vector V can be the summation of this equation. First term is the derivative of cost function, cost entry function. Second term is the derivative of softmax function. Third term is the derivative of output function. If we plug into them, we can obtain this total equation. This equation is the conclusion of the first part of my lecture today. This is summary. And for the simplicity of class, I'm going to only show a case where I is equal to J. At this moment, please forget that at this moment. And the more details could take more time, and for the purpose of the class, we don't need to do that. I'm gonna show you some basic concepts of backpropagation through time. I would like to summarize the first part of my class right now. So in order to update V matrix that is connecting the hidden layer to output, we have to apply this gradient descent equation. In order to do that, we have to derive the equation that dictates derivative of total cost function with respect to V. It has three parts. First part is the derivative of cost from cross-entry function. We know that it is represented by this equation. Second part is the derivative of soft function. And in those cases, we spend a little bit of time to derive this equation. That is described by multiplication of output yj, softmax output yj, 1 minus yj. And last term is the derivative of output function with respect to v, and then that is the hidden layer of k means the vector element of hidden layer at stage t. So by applying these three terms into this equation, we will have this back propagation through time in RNN. By having this back propagation through time in RNN, we can update a V matrix. So what we can see is that, okay, I'd like to update during the training process, I would like to update V vector element, V matrix element, then we can apply this equation. And then we need to know the derivative of total cost function with respect to V element of matrix. And if you know the true value at stage t, and also you know the output of the at stage t that is described by 1 minus yj, and if you have a hidden layer number at stage t, you can calculate the derivative of total cost function, and then you plug into this gradient descent equation, you can update V matrix. Let's come back to the first part of my class again. This is the overview of RNN backpropagation. And in order to do that, in order to apply the gradient descent equation, to apply the gradient descent equation, we have to find this derivative of J with respect to V. Just before I show you this equation, how did I obtain this derivative equation? Because I know this softmax function and all this matrix relationship and the cost function. From this equation, by applying the chain rule, I was able to derive this derivative. And so the flow is like this. We define the cost function. We know a hidden layer input, output, and if I know that input at stage t, and also we know true value yt2, by combining y2, y-2, h2, and x2, we was able to derive the equation of this derivative of stage 2. And then make a summation of all this cost function derivative, we can update this V. That is the brief summary of the first part of my class today. This is very tedious and very detailed mathematical expression of backpropagation through time. Maybe conventional machine learning engineer may not need to have all this equation. They just use the library and they can design the machine learning models. But if you want to be more confident on your models, I recommend to follow all this derivation process to be confident on your models and understanding of your RNN. This is the first part of class today. Now let's move on to the second part of the class, while I'm going to show you the derivation of a backpropagation equation for W. That it will be a little bit more complicated. Now, I would like to derive equation for matrix W. In order to do that, the process is a little bit complicated. I will divide it between path 1 and path 2. Path 1 is the case where t is 2. That means only we have 2 input. That is a little bit simple cases, but for the derivation and explanation class purpose, it may be okay. So now the back propagation is this way, then let's look at this. Derivative of cost function at t plus 1 with respect w, if you want to obtain that, first is that you have to obtain this. Derivative of cost function at t plus 1 with respect to yt plus 1. And in the previous slides, I show you it is a cross-entry cost function. We can obtain this function. So we plug in this equation into this term. Second term is that a derivative of OT1, we have to make a derivative of y with respect to O. And it is a softmax function. And in the previous slides, we obtained this equation. Third one is we have to make a relationship. We have to make a derivative of output function with respect to W. So W is the input that is connecting from previous hidden layer to the output layer. And then I will show you later the activation function of this t plus 1 is the tangent hyperbolic function, and tangent hyperbolic function is 1 minus tangent hyperbolic function square. So we're going to plug in the third term with 1 minus tangent hyperbolic function, and the derivative of input, this hyperbolic function, will be ht. So it has, in this case of path 1, we have 4 terms. Number 1 is the derivative of cost function. Number 2 is derivative of softmax function. Number 3 is the derivative of tangent hyperbolic function. Number 4 is the relationship between previous hidden layer ht multiplied by w is the input of tangent hyperbolic function. Because of that, derivative of this input will be ht. So we're gonna have 4 terms. An input of at and tangent hyperbolic function at stage t plus 1 is u multiplied by x t plus 1, that is this path, plus w multiplied by previous hidden layer ht. Derivative of this term with respect to w will be obtained the ht, that is the number 4. So what we found is that this is what we want to do. And that is the derivative of cost function with respect to w. If we make a summation from jt to up to the final, then that is gonna be total derivative of cost function with respect to w. And sequentially, we can plug in number 1 equation, number 2 equation, number 3 equation, and number 4 equation. And then finally, we obtain this equation. Derivative of cost function with w is the multiplication of true value and 1 minus output function and tangent hyperbolic function. And I will define that tangent 1 minus hyperbolic function is 1 minus delta t plus 1. That is the, I would say, definition of delta t plus 1 at stage 1, stage t. So now I define delta t plus 1, that is 1 minus tangent hyperbolic function at. At is defined by multiplication of U matrix with input and W matrix multiplied by previous hidden layer. So if you plug into this, we obtain the cost function. And if you a derivative of cost function gradient, then if you plug in that to here, you can update W matrix. That is the connecting matrix from each state to hidden layer to hidden layer. The rules are same. So if you, so the cost function is the summation of cost function. Total cost function is summation of cost function of each layer. So, what our task is to make a derivative of stage t cost function with respect to W. In order to do that, you just go through the path. At each path of transitions, we have to derive this equation because we know the softmax function, and the softmax function and cost function and activation function. We just apply this derivative of each stages, and we can, by applying the chain rule, finally, we can obtain the relationship of derivative of cost function with respect to W. This is the case only t equal to t2, but you remember that it will be continued up to the million times or billion times. You have to apply. In this case, we have only 1, 2, 3, 4 equations. But if you have a stage t is equal to millions, you have to derive all these million times of these equations. That is a little bit bad part of the RNN. So backpropagation takes some time. It is a slow process. And sometimes if W is a small number, it has to be multiplied by million times. Will cause the vanishing problem. If W is larger than 1, it will have exploding problem. So, again, this is a simple case of t equal t2. But as I mentioned that we may have million times or billion times. It has goes through back, and then this number will be a million or billion times multiplications. So it has go back to the first hidden layer. That's why we call it this back propagation is called back propagation through time. I would say here billion times. The derivation of backpropagation relationship with V is a little bit simple because we go from a cost function to up to hidden layer, but the derivation of gradient descent equation for W is much more complicated. It has to go through all the time. It takes some more time, and also compared to previous equation, it is a little bit simple. You see that it is a little bit simple, but here we have delta function, 1 minus tangent hyperbolic function, and that is a little bit more complicated. Now, let's continue this. In this case is where t equal to 3. Let's take a look at path 2. So in order to make a gradient of cost function with respect to W, we have to start from here, and here we have to know the cost function, and also at this stage we have to know the derivative of softmax function, and the relationship between output and H, we have to know the V matrix. To make a relationship between V to W, we have to go through tangent hyperbolic function. And also, when we go through this activation function at stage T2, we have to also have a tangent hyperbolic function. And finally, we reach to W. And also, we have to know this HT. So cost function F and softmax function derivative, we have to know that. Also, we also have to tangent hyperbolic function and tangent hyperbolic function, and then we have to know HT. This is the path for So here we see that why we need tangent hyperbolic function, because that is the activation function of hidden layer t plus 2 activation function. And also when this function is connected to ht plus 1, we have to multiply w, but also it has to go through another activation function, tangent hyperbolic function. This is activation function here. So that means we have to consider derivative of tangent hyperbolic function twice. Here is the t plus 2, here is the t plus 1. That is the derivative of activation function. So now, in the case of t equals 3, I spend time of this derivative of cost function at t plus 2. It has this term is applied so many times. Oh, something wrong? I will do that again. Probably because of internet. Okay. So here I would like to emphasize 말로 할게요. 아마 인터넷이 지금 잠시 그런 것 같습니다. 잠시만 기다려 주세요. 인터넷이 불안정합니다. 한번 다시 해보겠습니다. I will try it again. Right now, internet is a little bit unstable, so let me summarize this. This is the final summary equation for the case of n. So you see that delta is multiplied n times and w is multiplied n minus 1 times. And delta function is 1 minus tangent hyperbolic function. So to obtain the derivative of cost function, we have to go through this term. So delta has to be multiplied many, many times if you go back one state, one state, one state, one state, one state. That is called back propagation through time. So now let's take a look at this equation again. Let's assume you remember that W is multiplied so many times, and this delta is tangent hyperbolic function, so it is a range between 1 to -1, so we don't need to worry about that much. But let's pay attention to W. If W is smaller than 1, it is going to be almost 0. That means contribution of this cost function up to the W is not effective. The backpropagation has no meanings. Because this is RNN, you still want to remember first wording of your textbook up to the last wording, even though the number of wording is more than million times. But million times multiplication of less than 1 is become 20. So this RNN will not remember what you have said a day before or at the beginning of your book or notebook. In other sense, if W is larger than 1, it is becoming derivative, is becoming infinite. And it's computationally, it is meaningless and unuseful. So because of that, we have to come up with LSTM. And on Wednesday, I'm going to spend time to derive all those backpropagation equations of LSTM. That will be a little bit more complicated. And I hope you are more patient. And believe in that my derivation process is a little bit simplified, but concepts are, I think, correct. Later on, if you are interested, you can use this notebook and you can follow them. Thank you for your attention. And once again, I would like to say that in order to be more confident on your models, you should spend some time to derive all these equations of backpropagation. It could be DNN or RNN, CNN, or GAN. Whatever machine learning, you should spend some time to understanding the mathematical procedures. Thank you for your kind attention.